Here we want to be able to find maxima and minima. So if we give ourselves a nice visual of what a max looks like and what a min looks like. And then we want to remember that the derivative of a function measures both the slope of the tangent line and the rate of change at any instant in a function. So we're going to label this according to what the slope is doing. So if we look at this first one, this slope left to right is rising. So it has a positive slope when we think about tracing it left to right the same way we read English. And then if we think about the other half, it's falling left to right as we trace it. So this has a negative slope. And then the slope at any soft peak like this is 0. So the derivative is the slope and it would be 0 there. Same thing with a minima. It would be falling left to right. So if we trace it, the initial slope would be negative on that. If we think about the slope for the second part, it's rising left to right, so it's positive. And then any soft peak, like right here, would have a slope of 0. Remember, the derivative measures slope, so we would say f prime is 0 there. So with both of these maxima and minima, we do see a sign change for the derivative. For the maxima, it went from a positive slope to a 0 slope to a negative slope, and then the minima went from a negative to a 0 to a positive slope. So we're going to see if that pattern holds throughout and make some sort of theorem out of this. So the first theorem that we have in this box here says that if the derivative is positive, if the derivative is positive on an interval, that means the original function must have been increasing, right? Increasing functions have positive slopes. Positive slope means positive derivative. Derivative is the slope. If the slope is less than 0, however, that means the original function to have a negative derivative must be decreasing. So a positive function, or a positive derivative means the function's increasing. A negative derivative means the original function's decreasing, which of course can look a bunch of different ways, but there's an increasing line and a decreasing line. It could be part of a parabola like above. And then if the derivative, we plug in and we find that the derivative is 0 at an x value, that could mean a soft peak, like what we just saw above. Soft peaks have derivatives of 0, or it could be constant. It could just be a flat part of the graph. That has a derivative of 0, any horizontal line looking part of the graph. So if it has a soft peak, the derivative is 0. So at the top and bottom of a max and a min, the derivative is 0. And if there's just a flat part of the graph, that would also have a derivative of 0. So if we want to be able to figure out where a function is increasing and decreasing without ever even being given a picture, we can look at the sign of the derivative. So our two steps to figuring out where a function is increasing and decreasing, our first step would be to figure out where is the derivative 0, or where is it discontinuous, where is it undefined, where is its denominator 0. And the second step would be to test critical numbers between those x values where the derivative is 0. So if we test some x values on the interval and the derivative is positive, remember the derivative being positive means the function's increasing. It's rising left to right. If we plug into the derivative and we get a negative, the function is decreasing. It's falling left to right. So if we take a look at an example of this, we want to find all intervals where the function x cubed is increasing and where it's decreasing. So we're going to use these same two steps listed above. Our first step is to take the derivative and set it equal to 0. So we're going to take the derivative of the function and set it equal to 0. So our function this time is just x cubed. The derivative would be 3x squared. So we're going to take that derivative and set it equal to 0. So we'll take 3x squared and set it equal to 0. So we need to know some solving methods. So we want to figure out how to solve by getting x by itself. So we want to get x by itself. We would divide by 3 first of all. We get x squared equals 0. And then you could take the square root of both sides and see that x is 0. The other way of doing it, which I prefer, is thinking 3 times something has to be 0. That something must be 0. So you might have been able to recognize that as soon as you saw the derivative. 3 times something has to be 0. That something has to be 0. Or you could divide by 3 and take the square root of both sides and see that x is 0. So we have the important part to put on our number line for our second step is to test values before and after what made the derivative 0 or what made it undefined if it made the denominator of the derivative 0. So our second step is to test values before and after what made the derivative 0 here. So we have x is 0. That's our important number. That's what made the derivative 0. So we're going to put that on our number line first, and then we can choose any random test values to the left and to the right of 0. So to the left of 0, maybe I'll plug in -1. I want to see the sign of the derivative because the sign of the derivative tells me whether I'm increasing or decreasing. So I never would plug into the original on a sign chart. I'm going to plug into the derivative here. So the derivative is 3x squared. So I'm going to do 3 times -1 squared, plugging into this derivative here. So remember, you have to do exponents first. So -1 squared is 1. Times 3 is just going to stay 3. So it doesn't really matter the number we get. It matters the sign of the number. If you plug in -1, you get a positive 3 out. You get a positive number out. A positive derivative. Did that mean that the original function was increasing or decreasing? Positive derivative indicates increasing. It might not look exactly like that, but it is rising left to right. After 0, I can plug in any test value I want to. Maybe I'll just plug in 1. And I'm always plugging into the derivative because the sign of the derivative tells me whether I'm increasing or decreasing. So the derivative is 3x squared. I'm going to do 3 times 1 squared. 1 squared is 1, times 3 is going to stay 3. It's going to be positive as well. So we went from a positive slope to a 0 slope to a positive slope. So just kind of working ahead here, does it look like a max or a min? Well, a max is a positive to a 0 to a negative. A min was a negative to a 0 to a positive. So it doesn't really look like either of those. So we're going to see what happens when there's no sign change in a little bit here. But for now, I can just make a conclusion about where it is increasing and decreasing, which is all this problem asked about. We can come back and look at max and min in a minute. So for increasing and decreasing, we want to write our answer in interval notation. I'm going to start with decreasing because that's the easier one. This graph is never decreasing. It never had a negative derivative. So for the decreasing interval, I would just write none. And for increasing, we had a positive derivative before 0 and after 0. So my answer is not going to be negative infinity to infinity, because it's not technically a positive derivative everywhere. It's a positive derivative everywhere except for at x is 0, where the derivative is 0 instead of a positive number. So how I'd write that is negative infinity to 0. The round parentheses means excluding 0, union 0 to infinity. Before 0 and after 0, I have a positive derivative. At 0, I had a 0 derivative. So technically is not increasing there. But on the next page, we'll take a picture, get an idea of what this picture would look like and see what's actually happening.